Here we have table 1 0 0, then A plus and B minus has to be turned on. So switches H1 and L3 has to be turned on. Simply then rotor has moved to new position. We have new position 1 1 1 0. So new position will energize the C minus and B plus. It will activate the switches. This logic will activate the switches, that is L3 and H2. Then we have 0 1 0. This one. Now we have 0 1 0. Then we are energizing the B plus A minus. That means H2 and L1. L1 we select the phase A to negative. Similarly, we have 0 1 1 0 1 1. Then phase A minus and C plus. C plus will be activated. So for this we have H, D and L1 is activated. Similarly, we have 1 0 0 1. Now this 0 0 1 we can see here from previous figure at 0 0 1. Here 0 0 1. This is 0 0 1. Okay. So at 0 0 1, which one will activate? B plus and B minus. So here we have H3 and H2. Similarly, we have this 1 0 1. So at this condition, B minus and A plus will be activated. So with B minus we have the switch L2 and H1. So we now have the these table. What was the previous angle? Here previous minus angle was minus 30, and the new angle has become plus 30. After this, the previous angle was 30 degree. The new angle has become 90 degree. 90 degree. Previous angle was 90 degree. Then after this, in third logic, the new angle has become 150. The previous angle was 150, and by fourth logic, the new angle was 210. Now fifth logic, the initial angle was 210, and the final angle becomes 270. And from the sixth logic, initial angle was 270, and after the logic and application of the switching signals, it has become 330, or you can say -30. Okay, so now we will design this logic in the uh, Simulink. Now we will design this logic in the Simulink. So we have simply we have three signals. For this, we put here the permanent magnet synchronous machine from the Simulink, and we set the back EMF to the trapezoidal, because the BLDC motor is a trapezoidal back EMF machine, and permanent magnet synchronous machine is sinusoidal. So we have to set here trapezoidal. So it will act as the BLDC motor. We have the 6 switches that we obtained from the Simulink work Simscape specialized technologies. We have this one, and in power system specialized technologies, and from this we can have fundamental blocks, power electronics related switches, elements like branches, and other components. Here we have electrical sources, so we have taken the electrical source from here. So in this way we have set put all the components together, and we have inverter here. This is the inverter, and is it visual?
Yes,
Hello?
sir.
Okay. Okay, so here now phase A is connected to phase A leg, that is H1 L1 here. This is H1 L1, this is H2 L2. These are MOSFET switches, and we have this phase C. So now we have to design the uh, sensor logic. So our sensor logic from the motor model, we have the HA, HB, and HC outputs. So from here we use the bus bar, and from that we can find out all the values. Here we can select. Okay, we can remove, we can select here all, we can select, and one of three of these signals are Hall sensors. Okay, from here we will find the Hall sensor signals. So if we connect here, this is actually the here it is written HA. Can you see? Is it visible?
Yes, sir.
Okay, is it visible? So this is Hall sensor A, this is Hall sensor B, and this is Hall sensor C. For checking the speed, we can simply the rotor speed is find out here. We can see this rotor speed is showing in the radian per second. So we will finally get the response. Now we have three Hall sensor signals, which is obtained by tagging here. We have these three go to, and RAM blocks are here used here. Using these signals, we design now the Hall sensor logic. So greater than greater than 0 will define 1. HA equal to 1, and equal to 0 means 0. So HA, when HA equal to 1 and remaining are 0, 0, 0, then first A plus C, A plus and C minus signal will come out. This is the signal for A plus and C minus. So we have first signal 1 and this signals 0 and this HC equal to 0. This will energize the A plus and C minus. Okay. So this is first logic. Second logic is what I have written there. Second logic is 1 1 0. Okay. So first will be 1, second will be 1, and third will be 0. So from the 0 signal we can directly give here. Okay. This will energize the B plus and C minus. This will energize the B plus and C minus. Now we have another signal, third logic 0 1 0. So for this we have first one is 0, second one is 1. So we take from here, and third one is 0. So we are giving this 0 signal to this end. Why this end? Because when all these conditions are met, then this will happen. So means HA is 1 and HB 0 and HC is 0. Okay, clear? So now third logic is this fourth logic. Fourth logic is 0 1 1. So here we have first input as 0, means HA is 0. So we will give the signal from 0. Second one is 1 and 1. So we give the 1 and third is 1. Okay, clear? Now next logic we design 0 0 1. For this we have 0. First one is 0. So here it is 0. And second is also 0. So for this we have this 0 terminal. So we connect here. And for third 0 0 1. So for third we connect from 1. Okay. This upper side is HC equal to 1. Here HB equal to 1. Here HA equal to 1. Last logic we have 1 0 1. So for this we have simply this 1, second terminal is 0 0, second terminal is 0 here, and third terminal is 1. So third terminal will be connected to 1. Now this is for A plus and C minus. So A plus means H1, the same signal goes into the C minus, means wherever any signal comes, it will accept this OR input. Okay, so H1 and L3. Second one is B plus and C minus. B plus and C minus means first is C minus and B plus. Here same signal goes, B plus and C minus same signal goes. Means both switches are on, H2 and L3 are on. Now here third is B plus and A minus. So this is B plus and A minus. Okay, so fourth is A minus A minus and C plus. Fourth is A minus and C plus. So we have A minus. Where is A minus? This one. And C plus means this one, H3 plus. Okay. Next is C plus B minus. C plus B minus means we have C plus, we have H3 and B minus L2. Same signal goes at both places. Okay. Now we have B minus A plus. B minus A plus means we have this one, some mistake has happened. So simply like this, we will connect fifth was fifth logic is C plus or B minus, C plus. And hello, am I audible?
Yes, sir. You are audible.
C plus B minus. And last logic is B minus and A plus. Here some mistake has happened because B minus A plus. It should connect to B minus. Okay. Let's do it again. A plus C minus C minus B plus C minus B plus and B plus A minus B plus A minus A minus C plus A minus C plus and C plus B minus C plus B minus and B minus A plus. This one. Okay. So logic is completed. Now we see the performance of this logic. So here we have completely designed the logic based on the Hall sensors, starting from logic designing and understanding the Hall sensor positions. Now we have 6 signals here and we have to give these signals to the switches. So H1 will go to this switch, L1 will go to lower switch of first leg, H2 will go to this switch and L2 will go to this switch, S3 will go to this switch and L3 will go to this switch. Okay. So now we check is it working or not. So motor is properly working. Okay. So this is the simple logic. This is the simple logic which is used for moving the motor. Now when the motor is moved, we can apply the PWM techniques here. So open loop and closed loop control techniques we can implement. We have voltage follower technique, we have current control method. So simply if we apply the open loop control in this system, then what we will do? Simply we will generate a PWM signal here and superimpose with these energization signals. This is the fundamental signal which was coming from the logic signals, and from the fundamental signal, if we superimpose the modulate the PWM signals, then these switches will operate with the PWM. So for this, we simply generate some source. Here we have, simply we can take this signal. Okay, suppose we have the amplitude 1 and the period is this is sample based, time based. Suppose we have the period of this signal as 1:-4, means we have 10 kilohertz frequency. So time period will be this, and the duty cycle is suppose 20%. Okay, there is no phase delay. Then this will be the PWM signal. Now we can impose this signal with the fundamental signal. So for this, we have AND signal. So every signal will come to this, and one of the signal will be this. Okay, the same signals will be modulated to every fundamental signal, because this fundamental switching signal energizes the switch, and if we modulate the PWM in the fundamental, then the switches will operate with the PWM. So here one of the signal will be simply this. Okay, and this one, and remaining signals will be this, which operate the switches. Okay, so here now we can connect these signals L1, H2, L2, and H3 and L3. Okay, now we see what happens with the current. We also see the current. Suppose we are checking the phase A current. So up the most top side is phase A stator current. So here we can see the stator current. Okay. So now we simulate and see the performance of this control. So here the current is controlled. Current has some PWM part. We can see this 120-degree sector. This 120-degree sector of the current is on, and remaining 60 degree are off, remaining 30 degree off. So we have this PWM control, and it has a high ripple component, and this type of control cannot provide the appropriate torque and speed behavior, current behavior. So for this, we need to use the closed loop control using the DC link current. So for this, we will simply measure the current here. We have the current measurement system. I have the time now, because still the lots of things are remaining. So here we have the current. Okay, now we can use the current control method for the speed and torque control. Okay, so for the speed and torque control, we have the actual speed and desired speed. Okay, so from here we get the actual speed in RPM. From this signal we get the actual speed in RPM, and we have also a command signal. So for this we provide a constant input. Suppose we have the RPM of 1000. Okay, now we have simple the okay. We have simply the summing point. We can use this as, we can change this to negative, and here the actual speed will be this one. Okay, so now this speed gives the this gives the speed error, and according to this speed error there will be some current, reference current. Okay, there will be some reference current. So we use the PID here. Suppose we have this controller and we have some defined value. Suppose we use proportional value. Suppose at 10 ampere the motor operates to full RPM, so it should be according to that. So suppose your motor is 3000 taking 3000 RPM at 10 ampere, then the 10 divided by 3000 will be the proportional value. So it will ultimately result into the current value. Okay, so we also, if we reduce some proportional value, then we increase some integral value. So here you can say you can reduce to 8. This is the trial and error method. You have to say tune the PI coefficients, PI parameters, and after that you again use this block and now you feed the actual DC link current. Here you have the DC link current. Okay, so what happened, we have the current error, and according to current error there will be some value which will be this will give the duty cycle output. Suppose we have 1 ampere or 2 ampere maximum difference, then we can use some value. So this is totally the trial and error method. Wherever our control is good, we can be stable at that point. So other methods are there for tuning the PI controllers. Simply we can model this whole system, and using the model we can tune the PI controller. So using this we can use the hysteresis controller, or we can use the PWM controller. Okay, so in this way do I have the time? Still I have time.
Yes, sir.
So I would like to first show what are the control algorithms available for the BLDC motors, and then I will show you how the control algorithms are applied. So we have various stages of the motor. In the BLDC motor, we have part first. We can design the BLDC motor. Nowadays, slotless motors are coming. Bearingless motors are being manufactured, and inverter where we have various issues, sensorless control and commutation error reduction, PWM strategy, and device stress and losses reduction. So if we have the AC to DC system, we have AC to DC without DC-DC converter, and one of the converter is PFC converter, where we can also use the bridgeless converters. So uh, here the sensorless has censored algorithms have some problem that during the heating of the machines, the sensors generate the noisy signals, and they can damage, and sometimes they are not robust. So for that, we prefer the sensorless control algorithms. Also, we have the voltage amplitude modulation control or speed control, and with fixed voltage, we can also apply the current control method. If we use the limited duty cycles and then use the voltage amplitude modulation, that is called the pulse amplitude modulation. A certain frequency of modulation is used for duty cycles, and voltage is also controlled. So here we have various current control methods. So this is the constant frequency PWM generation, in which the fundamental switching signal is modulated with the PWM signal obtained using this. So just I was making the same loop, the reference speed and actual speed, and we have the PID, and the reference current was compared with the actual current, and the PID has given the duty cycle, which is compared then with the uh, triangular signal, and by comparing with the triangular signal, we have the PWM signal. With this PWM signal is ended with the fundamental switching signal of the switch, and it goes to the main switch of the inverter. Simply here we have the hysteresis controller. Here we don't need the triangular signal generation. We simply give the duty cycle directly to the hysteresis controller, and there is a certain parameters of this hysteresis controller. What is the maximum limit from the average point? What is minimum limit from the average point? That is called the H and minus H. So the logic is, if I minus I reference is greater than H, then it will be 0, and otherwise 1. I minus I reference is less than minus H, then it will be 0, otherwise 1. So it will be operating, it will not let the current to increase beyond the certain limit, and the current will be regulated. Here we have also the DC side, DC link voltage control methods, where we have the voltage amplitude variation, voltage amplitude, current source side voltage follower method, and uh, current multiplier control strategy. Okay, so here both the methods are different. Here we have generated the reference current, and multiplied it with the peak magnitude, and the source voltage and peak magnitude. Simply here we have the AC to DC systems using the bridgeless say peak and boost converters, top converters, zeta converters, CSC, and low converters, Landsman converter, where there are lots of modern converters also, which uh, provide the upgraded current ripple, uh, uh, means minimized current ripple, minimized voltage ripple, and minimized switching losses, voltage gain, and drive capability. So we have a typical system. We can see here this AC source is rectified, and there is a filter, a DC side filter, and DC side filter reduces the voltage ripple, and then a DC to DC converter is there. This type of converter may uh, stabilize the voltage in the DC terminals. Also here we can integrate the renewable energy system and storage system in the same point. We can also integrate the storage and uh, renewable energy systems. So here various methods are used. These type of various types of sensor and less algorithms may be applied. So we have the back EMF detection, flux linkage estimation, flux linkage variation and increment, Kalman filter, unknown input observer, sliding mode observer, robust stochastic observers, low torque observers, and adaptive observers are various sensorless methods. One of the method is detection based method, in which we use some filters, RC filters in the actual terminals of the motor, and from that we determine the back EMF, and from the back EMF zero crossings we determine the commutation signals. So we have also some methods in which if we have defined back EMF, then we get some ratios, and these ratios increasing very high at the commutation points. So with using certain thresholds can give us the Hall sensor signals, or we can provide us the commutation signals. Like here we have zero crossing here. So after 30-degree display delay, we have the switching of phase A. So now I come to the solar PV part, and I will not go more into the motor part. So here we have this solar PV model. So parameter model is basically the latest model which has been defined using the alpha. Alpha is identity factor, and RSE, RSH, diode, current, diode parameters, and this temperature and irradiance. So depending on these values, we have some equations which is obtained in literature. We have diode current, which is actually depending on the electron volts and identity factor of this. K is the voltage Voltman coefficient, and based on this we can calculate the IPV, the PV current. Photo current is actually depending on the temperature of the cell, and they are different with a reference temperature, that is 25 degrees centigrade, and we calculate it in Kelvin. So when we test any solar PV, we get its short circuit current, and depending on the short circuit current and its defined standard irradiance and standard temperature, we can determine the PV current, photo current at particular irradiance and particular temperature. So this actual array current will depend on the number of parallel modules and the difference of PV current and diode current. So the overall we have this complete equation which defines the array current, and depending on the series resistance, shunt resistance, number of series and number of parallel modules, and the voltage at the terminal of the array, and the current at the terminal of the array. So if we look upon the PV characteristics, the PV characteristics shows that the current increases in the same pattern.
Sir, we may have to go for another station.